and we're looking at scientific notation before we start evaluating our logs. So scientific notation has to do when the first number to the left of the denominator, to the left of the decimal is between 1 and 9. And then we multiply that by 10 to some exponent. It just depends on the decimal places that they're asking for. So you learn this in chemistry when you talk about significant digits, and you also do it in biology. So let's take a number and let's just kind of go from there. So if I take a number that I want to convert into scientific notation, so let's look at something like 45,000. So it's implied that we already have a decimal to the right of 45,000, and we are going to create scientific notation. So to do this, what we do is we now take this decimal and we want to move it right here. So we're going to go 1, 2, 3, 4. So in order to take the 45,000 and convert it into scientific notation, let's do this again. We want to move it right here, and it went 1, 2, 3, 4. It's like every jump is in between each number. So then altogether it becomes 4.5 times 10 to the fourth. And I have our calculator up so we can check it. So I have 4.5 times 10, and then 4 is the exponent, and I get 45,000. So now we're going to go from a decimal to scientific notation. So suppose I have 0.00076. Again, we want our first digit in our scientific notation to be between 0 and 1. So that means our decimal has to go right here. So we start right here because it's already given 1, 2, 3, 4. Now, because we went from a decimal to a whole number, this is going to be a negative 4 exponent. So as we present this in scientific notation, it's going to be 7.6 times 10 to the negative 4. Now let's see what that gives us in our calculator. 7.6 times 10 to the negative 4. There you go. So again, when you go from a large number to a small number, our decimals are positive. When we go from a small number to a larger number, our exponents are negative. Approximation of 4 decimal places. I went ahead and put parentheses around our argument, and I typed it into the calculator, so you do need a calculator for this one. So as you read it, it's going to be 0.4116, and that is a correct estimate. It says 4 decimal places. So let's go ahead and put this next one in here. We're going to go to log. You can type it in on your keyboard if you need to. So it's log 4.43 times 10, 10 to the second power. So then I get 2.6464. And it's 4 decimal places after the decimal. The next one is going to be log 307. And again, putting this in parentheses. Plus log 15. Let's make this wider. Log 15. So then we get 3.6632. And the last one So it's going to be log 675 minus log 203 or 203. And we had a decimal 0.51. Oops, we do that correctly? 657. Oh no, it's incorrect. 657 minus log 203. So our decimal is 0.5101 because that number right there, we get 0.511 or 10069. This number increases that by 1. The nearest tenth, when appropriate, use the formula pH equals negative log of the hydronium ion as needed. So this one is asking you to find the pH. So the way that you want to go ahead and break down the hydronium or the pH formula, we're saying the pH is equivalent to a negative log. And instead of talking about the hydronium ion, the H3O plus, we're going to call it X. This whole thing is now X. So we're going to have negative log X. Okay? And in number 5, it says, find the pH if H3O equals 5.8 times 10 to the negative 10. So this whole thing right here is H3O, which is also X. So we're substituting this whole thing in for X. So we want to say X is equal to 5.8 times 10 to the negative 10. So what we put in our calculator is negative log 5.8 times 10 to the negative 10. So this is what we're putting, this right here is what we're putting into our calculator. I'm going to get negative log and then 5.8 times 10, and then all that's going to be raised to negative 10. And it's asking for your answer to the nearest tenth. So that means our pH is going to be 9.2. And all this was equal to pH. And that's number 5. Number 6, find the hydronium ion if the pH is 10. So all we need to do here is a change of base formula. So make this larger. This is number 6. Our formula is pH equals negative log of the hydronium ion. Again, we're saying that X is equal to the hydronium ion. But then it tells us our pH is 10. So we also know that pH is equal to 10. So, so 10 equals negative log. Again, it's assuming that you know that this is going to be a 10 base X. So before I do this, I have to, I don't know why it's doing that, sorry. Before we do that, we're going to divide both sides by that negative because that's a negative 1 as being multiplied by log. So now I have negative 10 equals log of X. Well, when you do that, if we do a change of base, right? So you know that this is a base of 10. So we're going to say base is equal to 10. Then we know that the exponent is equal to negative 10. And our argument is equal to x. So that means we can say that 10 raised to the negative 10 is going to equal x. So now you know that x is equal to a large value, which is going to be 1 times 10 to the negative 10. So if we do that into our calculator, it should give us a scientific notation. Ten raised to the negative 10 gave us the answer 1 times 10 to the negative 10. The population, the growth of animal species is described by the function f of t equals 400 log times, it's 2t plus 3, where t is measured in months. Find the population of the species in the area 6 months after the species has been introduced. Okay, so t equals months, so t equals 6. And then your function is going to be f of t equals 400 log 2t plus 3. And it wants you to know what is going to be the population growth. So again, f of t, we can define this. F of t is the population growth. So this is what's important. Try highlighting it. That's important. That's important. T is months. And that's what it's asking you to find. So we're going to substitute this. We get 400 log 2 times 6 plus 3. And then we put that into our calculator. Let's see what we get. Oops. So we get 400 log 2 times 6 plus 3. And we want to know the growth of the population. So now we have f of t equals 470.436, but it's asking us for a whole number. I think that's the way it is in your book or in your online, so it's 470. That's the population growth. Okay, so this is ln. It says find the value given approximation in 4 decimal places, and that's what we're going to do. So this is just more calculator. ln is a different button than log. You're going to go into function. ln is to the left of the log button, so it's ln parentheses 815 times 34, and that's going to give us 10.22958. So 4 decimal places, 10.2295. Okay, the next one, ln, and then it wants a fraction. So that's going to be 93 divided by 23, and I'm going to get 1.3971. And then you have number 10. The logarithmic function f of x equals negative 100 plus 86 ln models. This models the number of visitors in millions to a certain country's museums, where x is the number of years since the initial recording of the number of visitors. Use a function to estimate the number of visitors in 50 years, round up to the nearest tenth. So this one is giving us to the 10th. So here's what's important. The formula, knowing that we're doing it in millions, where x is the number of years, the years are 50 years, and then to round our answer to the nearest tenth, but we're looking for the number of visitors. So x equals 50. F of x equals the visitors. So the f of x to figure out the visitors is going to be negative 100 plus 86 ln of x. So when we set this up, this is how I like to put parentheses, negative 100 plus 86 ln of 50. So that's what we're putting into our calculator to get the f of x. Okay, so negative 100. Ln also stands for natural log. It's in the notes. So 86 function ln of 50 is going to give us 236.4339, and it's asking us to round to the nearest tenth. So this is equal to 236.4, but remember this is millions of visitors. So if we had asked you to expand it, it would be 236400000. Those are supposed to be commas. So that's how much it would be if we expanded the number. So this says to use the change of base rule to find the logarithm to 4 decimal places. So the change of base rules basically means that you're going to put it into calculator a certain way. It's going to be log of the argument divided by log of the base. So we're going to read number 11. Log base 9, argument is 62.74. So our base is 9, our argument 62.74. And the way that it gets typed in or set up, log 62.74, put in parentheses please, divided by log of 9. So what do we get? So log of 62.74, parentheses divided by log again of base 9. Four decimal places is our solution, 1.8837. Number 12, base is 2, argument 0.61. So log 0.61 divided by log of 2. In parentheses, log of 2. So we get negative 0.7131. It's okay to get a negative. It doesn't really happen, but it's going to happen periodically. Okay, that's the end of